I'm going to present Bell's argument first. Originally, it's a statement about marginal probabilities of a joint probability distribution, but I find it makes much more intuitive sense if you talk about it as a game that two players are cooperatively trying to play. And so what is this game? And this is called the CHSH game after Clauser, Horn, Shimoni, and someone else. Sorry, I should have looked it up. And so here's the game. We have Alice and Bob. So Alice and Bob have migrated from cryptography to quantum information theory, if you want to know where they came from. And I don't know, so Alice and Bob are the two of the prototypical participants in crypto systems. So they're playing a game, and they want to cooperate to win with as high probability as possible. So you have a referee who doesn't actually make any decisions. He just flips coins and does what the instructions tell him. So sends a bit to Alice and Bob. So we'll have him send A to Alice and B to Bob. And then Alice and Bob, who are in separate rooms and cannot communicate, get these two bits and output two more bits, X, Y, 2 bits. And I should say the referee chooses his bits completely at random. So great. So now we need to tell you when Alice and Bob win and when they lose, because otherwise that would be, so we need to know when people win and lose to determine the game. So Alice and Bob win if X plus Y equals A times B, or I should say X plus Y mod 2. So that's A, X exclusive R, Y. Wait, no. Yeah, no, that's right. Okay. So that should be pretty clear, but I want to put up a little chart to make it, well. So A can either be 0 or 1. B can either be 0 or 1. And Alice and Bob win if X plus Y equals 0, X plus Y equals 0, X plus Y equals 0, and X plus Y equals 1. Now let's pretend that Alice and Bob have to do this deterministically. So Alice has a little chart. If X equals 0, output 0. If X equals 1, output 1, or something like that. And there's a general theory in games that in games like this, Alice and Bob cannot do any better with a probabilistic strategy than a deterministic strategy, and we'll get to that later. So here, well, here This is x0 plus y0. x0 being the bit that Alice outputs if A is 0. This is x0 plus y1. This is x1 plus y0. And this is x1 plus y1. And these are all mod 2. Yeah?
Oh, that was my question. Isn't it plus with a circle? Mod?
Yes. I am being lazy. Okay. So this is what Alice and Bob want. Now, can anyone tell me why they can't win with probability 100%? Yeah? That's right. So you sum everything up. So that's 2x0 plus 2x1 plus 2y0 plus 2y1 is equal to 1 mod 2. That doesn't work because, there's 2 x1s in this chart, 2 x0s, 2 y1s, and 2 y0s. Alice and Bob. Now I want to say Alice and Bob can only win with probability 75%. Probability. Why is this? Well, so there's no choice of x0 and x1 for Alice and Bob, or x0, x1, y0, and y1 that makes this perfect. So let's suppose that Alice and Bob have agreed in advance to some combination of x0, x1, y0, and y1. The referee comes along and sends them 2 bits, which randomly select one of these 4 boxes. Well, we know one of these 4 boxes has to disagree with what Alice and Bob want, because they can't all work. So at least one has to be wrong. And if one's wrong, and the referee picks that one, which he does 1/4 of the time, then Alice and Bob lose. So that's 75%. And now I want to argue why a random strategy can't do any better. So for a random strategy, we have probability that they win is equal to some probability of, let's let R be the string of random bits that Alice and, so a random strategy, you can always think of this as Alice and Bob get some set of random bits, and we don't care whether they're correlated or not. And then for these random bits, they pick a deterministic outcome of, x0, x1, y0, and y1. So the probability that Alice and Bob win with a random strategy is equal to sum times the probability of string R random bits times the probability that Alice and Bob win given R. So this is essentially an average of how often they win given any particular string of random bits. So if this was greater than 3/4, there must be some string of random bits which gives Alice and Bob a deterministic strategy of winning with probability at least 3/4. And we just argued that was impossible. So so that's the classical part. So now we want to say that if Alice and Bob have an EPR pair of qubits, 0, 1, minus 1, 0, then they can win with probability larger than 75%. But first, I want to say but I'm going to, the problem with 1 over 2, 0, 1, minus 1, 0 is that Alice and Bob get opposite answers every time. And I find it much harder to think about getting opposite answers than getting the same answer. So I want to find a way that Alice and Bob can arrange to get the same answer.